Okay, we are very happy to have Mia. Oh boy, I actually never. Shiki. Mia, I know Mia since the really old days when she was still a undergrad working with our dear friend Jumbo. And even then, she struck me as kind of the the enlightenment woman of computer vision, because not only did she read all the right computer vision papers, but she also knows a lot about art and humanities and just has a very broad perspective on things. And so the projects that she has been working on are always kind of very, Renaissance. And it's so always wonderful to see what Mia has been up to. She is a grad student with our dear friend Carl Wondrich at Columbia, and she's going to talk to us about things that, even though they involve language, I'm still thinking I'll approve of them. So Mia, welcome to Berkeley.
Thank you. Yeah, thank you for having me. I'm really excited to be here. So what originally got me into computer vision and machine learning was this excitement for teaching machines the skills that humans have. At the time, it was very satisfying to sit around and think about all the original and niche capabilities humans had and to try to see if we could get a model to replicate them. And today we actually have really incredible models that are capable of understanding and seeing the world in a very similar way to us. We've taught them the world, and now the question, naturally my curiosity sort of shifted to, okay, can we get these models to teach the world back to us? Maybe beyond what we originally taught them. So concretely, this means, can we get these models to do discovery? Can we get these models to provide humans feedback with respect to their learning objectives? Right, so the majority of computer vision tasks, such as segmentation, recognition, tracking, whatever you may want, these are tasks that humans could do, right? The reason we build these machine learning models to do them is for efficiency, temporal and financial. You could get a human to go and label everything every single time, but that would be too expensive with time and finances. And actually, Picasso, he sort of foreshadowed this. He said actually, computers are useless. They can only give you answers. So he foreshadowed that we would be using machines to sort of just replicate things we already know. And in this talk today, I'm hoping to convince you that maybe he was wrong. And I'm also hoping to inspire you to work in the opposite direction. So this paradigm of machines teaching humans, I've tried to disentangle into 3 branches. The first branch is obvious, it's discovery. So there's been a bunch of work in this area. Maybe the most famous one would be protein structure prediction with AlphaFold. Also last year at ICCV, we published this work called Muscles in Action, in which basically the idea of this work was, given a video of someone moving, can we predict their muscle activity over time? So for 8 muscle groups, we were predicting how much is that muscle activated, when, and yeah, basically that. And we also reconstructed the opposite direction. We said, can we reconstruct motion from muscle activity? So now you essentially have this motion generative model where the bottleneck is this representation of muscle activation. And what's neat about this is that if you have a bottleneck of muscle activity, you can encode a motion, right? And then you can take the predicted muscle activity for a particular muscle group, and you can actually edit it, right? You can scale it up or down, and then reconstruct a new motion that's similar to your input motion, except now it's edited to avoid or target a particular muscle group. And this brings me to my second branch, which is feedback, right? So in this particular project, feedback, like I said, you would have this input motion, you would predict the muscle activity. I'm only showing 2 muscle groups here because for visual purposes. So here you have hamstrings that are not super activated, as you can see with the yellow coloration. So I just take the prediction and I multiply it by some scalar larger than 1, I think 2 or 3. And now we see that the hamstrings are more red, right? They're more bright. And then I reconstruct. So I use my second model that reconstructs motion from muscle activity. And the reconstructed motion is the motion that is similar. It's also a squat, except the legs are further apart, thereby further engaging the hamstrings and the quads. But this is for just that project. I actually think that this problem structure should be worked on more generally, in particular with respect to leveraging all the knowledge that these pre-trained models have to tease out feedback for humans. So right now we have this ongoing work where we're saying, okay, can we capitalize on the knowledge in pre-trained language models, as well as a bunch of videos on the internet to sort of teach a person how to improve a particular objective. So for example, if you were to take gymnastics or yoga, and can you Google common mistakes in yoga, take those videos, learn from those videos, and then give some visual feedback on how a particular person should be improving their motion. Yeah. So the difference here is that this is like almost like human constructed. With sports, we have invented these rules, whereas with the first project, it's just biology, right? But I think this problem structure is interesting in many more directions. And then finally, the last branch is interpretability, which I count as machines teaching humans because it's machines teaching humans how machines function. And so maybe the most famous work in this area, in computer vision at least, would be GradCam. So this is like in the area of post hoc interpretability, where you're trying to visualize which features contribute the most to the classifier's decision. But also there's this other area of interpretability, which is interpretability by construction. And a good example of this would be concept bottleneck models. So this structure is essentially saying, okay, given an image, we're going to first go ahead and predict some textual attributes from a predefined list of attributes. And then we're going to have a second model that's going to predict the class from the attributes. And so by having this bottleneck, you're actually creating interpretability by construction, because you can then go ahead and see, okay, which attributes were activated, how much, and so on to understand the classification.
Oh, I have a question on the first branch. When you talk about discovery, like I guess the AlphaFold example is clear, but then what is being discovered in the muscle group?
Yeah, I should have elaborated on that a little bit more. So actually, knowing which muscle gets activated for a particular motion is an open question in the movement science community. We've sorted out the biomechanics, but each person has different muscle habits. And so the discovery element here is, what about you specifically? Like, what are your patterns? So if I collect a small amount of data on you, let's say half an hour data, can I now predict, given a new motion that you've never been doing in the training set, can I predict which muscle groups you're going to be using? And that's really useful for a bunch of downstream applications, such as digital therapy and so on, but you're discovering your particular habits. Yeah.
We know that if the feedback is right or wrong. For example, if the computer teach me that I just did something wrong, how do I know that if that feedback is actually valid or not?
In which project are you?
Like the second one.
The second one?
Yes.
Yeah, that's a good question. I can talk about like how we're structuring that problem right now later, but the general high level idea is we're using a language model to say what are the common mistakes, and we're creating a synthetic data set using text to motion models to create now like pair data of like, okay, you have this expert, you're going to corrupt it in this way using the wrongness from this language model, and you're going to train on that. And now we have like some data that we got from the internet of like people doing things incorrectly, and we're going to test. So it's going to be qualitative, but also we're going to evaluate on that synthetic data set. So I agree that it's not perfect, but so qualitative and synthetic actual numbers, because we have that pair data from that.
Thank you.
Yeah. So anyway, today I actually don't want to talk about any of this. This is just a little background on like how I got here. Today, the project I want to talk about sits right in the between discovery and interpretability. Right. So before I dive into it though, I figured I'd do a little review of clip classification, even though everyone in this room knows how this works. So you have this image of tiger, and the question is, how would I classify this image as a beach, a tiger, or a syringe using clip? So what you would do is you would encode this image with the image encoder, and then you would check the similarity by doing the dot product with the text encodings of each of these words. And then you would check which one's highest, and that's your classification. Now that we have that covered, I'm a big fan of games, so I figured we could play a little game to warm up the intuition for the problem. Let's see. All right. Okay. Can you see this? Yeah, we can. Okay, great. Right, so on the left here, we have two images that are representative of class 0. So there's many more images here. I'm just only showing you two. On the right, we have two representative images of class 1. And then down here, we have the accuracy. So since it's a binary classification problem, random is 50%. I'm going to ask the audience to give me a word or a couple words for text 0 that would help me classify between these two classes. And I'm also going to ask for some text for the second class. Does anyone want to volunteer for the one on the left?
Ocean?
Ocean, sure. Okay. And then so the accuracy is going to update. Does anyone in the meantime want to give me, it's usually faster than this. Okay, 80%, very nice.
Mm-hmm.
Anyone want to give me the other text?
Green.
Green.
Very abstract.
I mean, color is pretty abstract.
Yeah, you guys are 100%. Very nice. You guys are really good at this game. Really great. Good job. But actually, huh?
Blurry background.
Background, yeah.
Wait, sorry, why couldn't we have just said fish and bird?
Thank you so much. Is that what I wanted people to say? Normally when I play this game, that's what people say. So I'm gonna go with what you said. And
See, the problem with live demos, you have adversarial audience and.
Fishy green both work.
they work, but I just have a story to tell, and I'm
Okay.
trying to go through it. So I have an agenda. So all right, what happens if we take what this gentleman said and we apply it to these classes, right? So this is a little bit tougher. We're gonna now go ahead and take the common names. Sorry, let's start with the scientific names. This is for my naturalist, two separate species, and let's wait for it to compute. Okay, 55%. That's not very good,
So
right?
just clarification, so is this taking the embedding of those two texts and then classifying based on whether the image is higher dot product eclipse space with one embedding versus the other?
Exactly. So for each of the images, and all of them, really, you're just checking the embedding between these two, and you're checking which one's higher. And it's
Okay.
correct if it's, this one's higher for that one, and this one's higher for that one.
Is it clip fine-tuned on scientific names?
No, that's a really good point. So that brings me to why does this not work, right? Because CLIP has been trained on like the internet, basically. And so concepts that are commonly appearing on the internet are going to perform better, but more rare or specific concepts are going to perform worse. But you might be thinking, okay, well, Mia, you use the scientific class name, which is a little weird. Why don't we just use the common name? So let's try that. And now we actually bring the accuracy down to 50%, so totally random. And furthermore, not only does this not have a good accuracy, but we also don't really understand why it doesn't work. All we know is that the dot product between the images and the text didn't, dot product in the way that we wanted it to, for this one specific textual encoding. So if we thought back a little bit to the slide where I was introducing machines teaching humans, for the interpretability by construction, we talked about concept bottleneck models. And what was neat about that is that you actually had this bottleneck where you can have interpretability because okay, well, it was weighted this much for this attribute, weighted this much for this attribute. So from my lab actually last year, or a little bit further than a year ago, my lab mate Sachin had this work called classification by description. And what he did is he said, okay, I'm going to prompt GPT-3 given a class name. So for example, in this case, slender orange bush. And he said, let me have the visual attributes for this class, right? So it's cut off a little bit, but you get the gist. He has the LLM for the visual attributes, and what he did now is he took the mean of the CLIP scores. For this image, he took the CLIP scores across all of them and took the mean, and that's your new score. And what's neat about that is like before you take the mean, you can actually see the contribution of each individual attribute. And you can see, oh, this attribute was very helpful, this one was not very helpful. Okay, so let's try that. Let's try his method. And we're still at 50%.
So wait, sorry, how did you get these attributes?
You just prompt GPT-3, you just say, okay, what are the visual attributes for a slender orange bush? And then it gives you these. And these are correct, actually. I mean, the GPT-3 does really well at giving visual attributes for any sort of class.
But it doesn't know about the other class, right? So it's not what are the different attributes included.
Very good point, very good point. I'll get to that a little bit later. But yeah, so it doesn't work very well.
Do you think that part of this is just because these are very long, like descriptions? Like,
It's true. I mean, there's been some work that shows that Clip kind of treats sentences as a bag of words, so it doesn't really matter what the order is. So actually the fact that it's longer might be better, but I'm not sure. I don't want to anthropomorphize. So I just want to show I'm not cheating. Here's what happens if I put the scientific class name. We're also at, please load, and 55%. Okay, so this is not very good. Here's the fun part of the game. Let's see if we can do better. So I'm gonna put some blank attributes in here. Can I get a volunteer for the left side for one text?
Orange.
Okay, not very discriminative, but sure. Still better than 50%, I guess.
How about orange, not yellow?
not.
Ooh. Wait, I thought the not is not gonna work for
Yeah,
Clip.
Yeah, it's not gonna work.
Oh,
really,
you're
but
right,
Yeah.
yeah.
But, like,
Yeah, interpretability, huh?
I mean, the images on the left are like more like branchy is the wrong word, but it looks more like a bush.
Okay, let's do that then. Bush,
How,
bushy,
how about like, what is it called, loofah?
loofah.
The
Okay.
thing in the.
Do you want to replace one of them?
Huh?
We only get two attributes.
Oh,
Do you want
I
to
see, I
replace
see.
one?
Let's
Should we
kick
replace
out
No,
one?
no, no, let's do this.
No, no, no.
Bush is good.
No, I like, let's try. This is the whole point. We're just playing around. We can mess up, we can learn. That's okay.
What do the percentages mean on the,
Sorry?
what do those percentages mean?
Oh, that's the contribution. So I take the softmax over the
Okay.
scores of the dot product of each.
Like loofah.
And then on the right, anyone want to give some words?
Bark.
Moss. Fungus.
Okay, we're down to 50%. Let's replace
Oh,
some stuff.
no.
Let's try again. Come on.
Well, what if we just put that on the other side then?
Should we flip? Really? All right.
Put bark, replace bushy with bark.
What? I don't know about that, but let's play. Let's learn.
Yeah.
That's the opposite.
Yeah, replace bark with bushy.
Oh. Oh, okay. I see. Sorry. I get it. Yeah. Okay. Worse. Yeah.
Oh, wow, you're getting worse than chance. Good job.
I also want to contribute, maybe. New people.
Hmm.
I'm gonna start calling on people, so someone has to volunteer. Yvonne.
Oh, man.
Hand.
Oh, hand, yeah, sure. Why not?
Well, these are representative, right? So you might not wanna, it's like, there's many more images. These pictures.
Sponge, is the second one spongy? I can't even tell. Maybe spongy.
Which one do you want to place?
Moss.
Okay. Oh, guys.
Oh, man.
You guys-
Oh, my God.
But actually, this,
Reduce
all right,
that.
let's move on. That's okay, actually, this works into my point. So
Humans are really sucky at explaining things.
Berkeley
Yes.
especially, so
Plain things we
usually
don't
people
understand.
get like at least a 60 or 70%. But that's okay, because the point here is, or what are the lessons learned? The lessons learned are, one, coming up with descriptions is hard, right? It wasn't easy. It's really tough to sort of look at something visual, and Alyosha, you're gonna like this, and find the right words to sort of describe this, right? It's more easy to find an analogy or to be like, it's like this, so on. So coming up with descriptions is hard. The second thing is, usually with the right people, iterating is helpful. Right? Usually people learn and we get better and we collaborate and that goes well.
We sort of got up to 60%.
Oh, we did?
Just the opposite.
Yeah.
Oh, we did flip it and didn't, oh, we didn't flip everything. You're right, yeah. Well, that was adversarial, but yes, iterating is helpful one way or another. All right. So what's the key idea with this from the lessons that we learned? Descriptions are hard, iterating is good. Well, to me, that sounds like we should learn these attributes, right? Instead of using a zero-shot prompting method to find these attributes, can we actually learn them? Okay, so like what would be the goal? I'm just going to show this whole talk with binary classification, but in the actual paper, it's multi-class classification. It's just easier to explain this way. So let's randomly initialize some attributes for class 0. Let's randomly initialize some attributes for class 1. And then let's find some optimization procedure that eventually is going to get better. So what's the objective here? Well, let's just go over quickly what the score for one particular class is. So you're going to have phi, which is representative of some vision language scoring mechanism here. And then you're going to have an attribute, you're going to have a bunch of attributes, you're going to sum over them. Each attribute has a score with the image, right? And so then you're going to take the mean, so you're going to sum them and divide by the number of attributes, and that's your score for class C. And you can think of that as sort of like the logit indexed at class C, but you can do this for all the classes, right? And then so now you have like a logits vector. And you have your ground truth. You know what class it really is. You don't know the class name, but you do know what class, like label 0, 1, 2, 3, etc. it is. So now you know what your objective function is. Okay, so what would be the first thing we would probably try? Let's say we used gradients to do latent space search to find, the nearest. You would go in the continuous space and then you would latch on nearest neighbor to the discrete attributes that would work best. We could do that, and we implement this as a baseline, but generally speaking, language is a discrete modality. So searching in continuous space and then latching on to a discrete nearest neighbor isn't ideal, and you can run into a lot of like local minima problems. So what if we instead actually optimize directly in the discrete space? One approach to doing that, let me just quickly skip to that you know how this works, prediction explanation. Okay, so what about gradient-free optimization? One way we could do that is using an evolutionary algorithm, for example. The problem with evolutionary algorithms, though, is that the mutation step was designed for numerical optimization or combinatorial problems. So before I get into what that means, let's do a little review of evolutionary algorithms. It's the easiest algorithm in the world. So you have a population, and these are just data samples, and each data sample has a score, right? And you're going to normalize these scores to get probabilities, and with these probabilities, you're going to sample some candidates. Say we sample 10 of them. What you're then going to do is you're going to mutate these 10, and you're going to evaluate these mutated 10 with a fitness function. And then you're going to put them back into the population, these mutated samples with their score back into the population, and you loop. Okay, so what does that mean for us here? So we have a classifier bank. So one classifier is defined as like one depth layer here. You have some attributes for class 0 and some attributes for class 1. And each classifier is a data point. And they have a score, right? Because we talked about using that loss function with the logits and the correct class name. And so let's sample some classifiers. Except what we're going to do here is we're only going to sample, we're going to sample the classifiers, but we're going to extract just class 1. And we're going to sort them in decreasing order of loss. So the loss is going to get better and better. So the attributes are going to get better and better, and the loss is going to go lower and lower. And this is the key idea. You can't mutate naturally with language. So what if we actually just ask a large language model to generate us the next set of attributes? So this is in context learning. I'm sure you're all familiar. And we do this on an open source language model, Llama. So then, okay, now that we have this mutation, let's go back to the sample of classifiers we had, which you remember classifier has class 0 and class 1. We're going to replace all of class 1 with this new mutated class 1, right? And we're going to reevaluate using clip and with our training set. And then we're gonna add it back into the classifier bank. And we're gonna iterate like this. I'm gonna pause here for questions before I move on, if anyone's confused.
How do you augment the terms?
How do I augment the terms?
Come up with the new terms? By,
Like, she's prompting Llama 2 to
Yes.
come up with new terms.
Yeah.
So it's like give you an example of the old terms and asking for new ones.
like similar to the. Can you?
Yeah, sure.
describe
So
what
you know how you can prompt a large language model to give you something? My prompt is saying, look at all these examples. This example is the worst. And then eventually, this is my best example. Can you come up with the next
better?
example? Exactly.
Oh, I see.
Yeah. Cool. And that's called in context learning. Right, so we insert them back into the classifier bank. Okay, so let's like take an, oh, yeah, sorry.
Yeah, so do you keep like class zero's attributes fixed and only mutate one class at a time?
That's right. So, I mean, in practice, I parallelize this with batching.
Okay,
But yes, in terms of what the LLM sees, it only sees one class at a time.
okay. So it would be like a little different from how we were playing the game where we were changing both sides.
Yeah.
Yeah, okay.
Good point, good point. Totally.
But here you know the answer, right?
What do you mean I know the answer?
So your laws tell, like, you know what the actual classes are.
You know what the classes are, but you don't know the class names. So you just know that like these images, like this class 0, you start out with not knowing anything about it, right? You started with totally random attributes for class 0.
Oh, I see. So you basically, it's kind of like the score of the game. You know
Exactly.
the score, but you don't know anything else. I see,
Exactly.
I see.
You're blind, basically, but you have this information from the score.
Okay,
She's
okay,
like trying to solve an inverse problem, basically.
Yeah.
okay,
Exactly.
okay.
Okay.
So it is exactly like the game.
It is
Okay,
very
okay.
similar.
All right, all right.
Well, yeah. Okay. So I think what I really want to stress here is that we start out with 0 prior information. We just know that these images correspond to class 0, and then it starts out with class 1. So at the beginning, so here let's
Oh,
do
but
it.
you're looking at the pixels, right?
Yes, yes.
Okay,
totally.
okay, so it's not zero information.
Well, okay, but I'm saying you have no prior information besides the visual information,
Sure,
I
sure,
guess.
sure,
Whereas like all the baselines that I was mentioning before have class names.
Sure.
I have class names with attributes capitalized, gotten from a knowledge base of GPT-3. Here, we're really starting from just pixels.
Okay, okay.
And so
As one should.
as one should.
Yes.
And so iteration 1, this is what you start out with. So you start out with dark green leaves, often located in remote rural areas, a boom for lifting, vehicles, green coloration, a wide mouth, long curved dorsal fin.
This is
Okay.
just sampling from the prior.
So
Sorry.
yeah, I'm almost there. Just that, okay, it's kind of weird that there's dark green leaves and dark green coloration. That's probably where you're saying something.
Yeah.
Yeah, so when I initialize my classifier, I initialize 1,000 classifiers, and then I just filter for the top 50. So it's not gonna be very close, and also even if it's green, it's not very discriminative because all of these are green. So there's gonna be some vague similarity, just because I'm picking the top 50. So obviously, even when you do random and you pick the top 50, there's gonna be some similarity, but it's not gonna be nowhere near good enough to discriminate this between all of these 4 classes.
How do you initialize the attributes that the classifiers are using?
Very good question. So we have a pool of 10,000 attributes that we get by basically prompting GPT-3 to give us generally visually descriptive things. And so just you have all these random words, and then you're just gonna randomly pick up 6, randomly pick up 6. And I do this again for class 0 and class 1. That's one classifier. I do it 1,000 times. And I pick the top 50. It's my initialization. It's pretty naive initialization, but that's okay because we're learning. And over time, as this converges, we end up with much more descriptive and discriminative attributes. We have fragrant trumpet-shaped flowers, twisted curved branches, a tree with unique spiral pattern bark, leaves with a silvery sheen, long thin leaves with a velvety texture, and chef's quiz leaves with a hint of pink. So these are pretty good, I would say. And also I'll show the quantitative results later. But I think what's important to know is you're probably wondering what's the difference between free training and joint training. So this was pretty important to getting this to work. If you were to start optimizing just with these 5 classes, any attribute that is common to the 5 classes is going to be penalized, right? because it's not, right, exactly. But the problem is like, if at the beginning of training, when you're starting with totally random attributes, you're already penalizing anything that's common, it's gonna come up with very spurious stuff. So you might say like class 3 is slightly more ducky than every other class, even though there's no duck in there, right? So my trick to getting this to work was to say, okay, what I'm gonna do is I'm gonna take each individual class and I'm gonna actually do optimization with 4 other totally random things, like random, like dolphin, house, whatever, coffee cup, etc. And I'm just gonna do some pre-training and find the visual attributes for not fine-grained classification, essentially just regular classification. And that's my new initialization for this class, right? So now I have like a new pool of words that I'm gonna re-initialize my classifier from, and I'm gonna start over now, doing fine-grained classification. And so it's gonna start with these common things, and then it's gonna become discriminated from the basis of knowing, okay, this is probably a tree, or this is something like embed the vegetal space, right? So that's that.
Wait, just so
Yeah.
I make sure I understand. So your pre-training stage, you're comparing it to like, this is coarse grain classification, you pick like random classes?
Random classes, yeah.
Okay, so that gets it in the right mindset of like, oh,
Yeah.
we're doing plant classification or
Exactly.
something. And then your joint training
Yeah,
helps get the more fine-grained features.
exactly. It's like course define, yeah.
And so in your setting, like when you start and you prompt GPT for like all these like random attributes, you don't give it the class names,
No.
right? Have you, even if you did have the class names, like in some application, do you think it would not be advantageous to give those to start off? Like, do you think it would just like converge to some, like, it like wouldn't find as many unique things if you tried to initialize with the class names?
Oh, I see. You're saying what would like would it make it worse or better?
Yeah.
So actually, when I initially did this, and I was just doing regular classification, a lot of the time it just finds the class. So it's like if you do a dog versus cat,
Yeah.
it'll converge on dog versus cat. So it's like, first of all, it's not great to initialize with prior information because the whole point is discovery.
Right.
But second of all, it does converge on this like decision boundary part, right? What I've not done is I haven't tried basically just starting from fine-grained classification with the class names.
Mhm.
I wonder what would happen with that. I'm sure it'll learn something better because like as you saw, that doesn't work very well with clip, but it's a good question. Yeah, I don't know, I didn't try that. Okay, so let's evaluate. Yeah, so iNaturalist is a fine-grained classification data set in the natural world for plants and animals. And so what we did is we picked 5 families. So the lichen families, mushroom, Ross is a fish, velocity are plants. And so within each of these families, there's 5 to 7 species. And so I'm going to quickly go over the baselines. So the zero-shot attributes is just taking the attributes from classification by description, except we're not going to append the class. So they append the class, we're just going to say, okay, forget the class, just what are the attributes? Let's use those as our attributes. And the second one we're very familiar with, it's class name. We report like the best between common and scientific because iNaturalist has common and scientific. And then we obviously do classification by description. And then we also have a gradient-based approach in which what we're doing is we have like those 10,000 initial words that we start out with, and we have a probability distribution over that, and we're optimizing to weight eventually in a more sparse way to get the 6 attributes through the latent space with a loss. And then there's our method. And the blue ones are all baselines that have prior information, and then ours obviously don't.
So
Yeah.
what is the like upper bound by just like fine tuning the model on the training data without the explainability part, interpretability part? How good will it be if you just?
Oh, if you just fine-tuned clip.
Yeah.
I don't know. Good question. Yeah, I didn't try that. But I think the purpose of this work really is methodologically discovery and interpretability, not so much performance.
Say again, what is the gradient-based approach?
Yeah, it's basically just saying, okay, like let's initialize 10,000 words with a like equal uniform like, actually, what we're really doing is we have many more words, but we use the 10,000 that we used for our method and we weight them slightly higher to give it a little boost. And then we just use the loss from the cross entropy loss to guide back the weighting of these different 10,000 terms. And eventually he has like so a co-author implemented the baseline and he has some regularization to enforce it to pick closer to 6 attributes, weight 6 attributes more.
Okay, I see. So I see. So the parameterization is like the weighting on the word.
Exactly,
Okay.
yeah, exactly. Yeah.
Okay.
I don't want to take up too much time if you have. Okay, so just really quick, I don't know if you already answered this with my previous question, so sorry if I misunderstood. But if you took like the 0-shot attributes, let's say you like prompt GPT like multiple times at like a low temperature so
Yeah.
that you get all these different attributes, and then you use those as like you're starting off.
Sorry, are you
points.
prompting GPT-3 with a class name?
Yeah, so like you're
Yeah.
like the way you get these 0-shot attributes is with the class name.
Yeah, okay.
Right? So you do that, you do it multiple times to
Yeah.
get like different attributes.
Yeah,
And then you use that as like your initialization.
sure.
And then you do joint
Yeah,
training.
yeah.
Do you think this would work?
I think it would, but I'm really focused on not giving prior information because I
Yeah.
think the whole point of this method is discover and interpretability for things we may not already know. So right now I'm showing it off on iNaturalist on this other data set I'm about to present.
Yeah.
But the goal is to have this be useful for people who are doing discovery.
Yeah, no, it makes sense.
Yeah.
How did you, oh, sorry. Just interrupted
Sure.
everything. How did you choose the 5 classes to?
Well, these are all 5 classes that have between 5 and 7 species, or 5 families of between 5 and 7 species. And this actually does, the downside of this method is that it does take time. So just optimizing, like for example, one family took 8 hours on 8 GPUs on an A100 machine. And we got this to work 2 months before the deadline. So just some, or sorry, we started working on those 2 months before the deadline. So, just time. Yeah.
I'm still a little confused. What is the interpretability part of this? So how do I interpret this? What does this tell me?
Yeah, I think the interpretability bit, there's one thing that I'll keep as a surprise answer because there's another slide. But the obvious thing here is more just that it's the same idea as concept bottlenecks, where when you have a classification, you can see why it was classified in the sense that this attribute contributed a lot to this decision. This attribute did not. This attribute actually hurt the decision.
And the attribute here is just word.
A word, yeah. Because
Okay.
you have like 6 words, right? And you're
Okay.
taking the mean of the clip score of each word. So you see how much each word contributes.
But this has nothing to do with the pixels, right? It's just the word part of
Well, the
what.
score of the word has to do with the pixels because you're scoring between the word and the images with clip.
I see. But it could also be that just the word is actually not in the pixels at all, but the word correlates with some other word which is in the pixels, right? So it might be that the word actually is not connected with the pixels at all. You see what I mean?
It could be, but generally speaking, I think we take the assumption that the attributes that are discovered that are the highest or the best are going to be ones that are in the image. And I'm going to show some qualitative examples that sort of reflect
I see.
that.
Okay. Because like happiness, for example, is
Yes.
probably not in the pixels,
But it's not
but it's
gonna be
correlated
discovered.
with other things, huh?
But then it probably won't be discovered.
I see.
Because it's not
I
going to
see,
have as high of
I
a
see,
score.
I see.
So if you gave people who look at plants, the descriptions that you discover,
Yeah,
and then let's say that they're naive to the particular class,
sure.
and you give them 2 images.
Yeah,
And then you say, well, can you use this to do this classification?
exactly.
Because you're in, I think, discovery, helping human space.
Exactly.
Question mark.
Great question. We are in the midst of doing some human evaluations. So good point. Yeah. Anyone?
So is the downside of the gradient-based approach mostly that you have a fixed set of classes that you're optimizing over, or was it just like I feel like you can overcome the discrete sampling thing, gradients, so
Totally.
like, is it feels like it's mainly the input space
There's a
or?
couple of downsides. The first is that the larger that you make your bank of like searching, the longer it's going to take to converge on the finer thing. I think this converges way faster. The second thing is we just tried, and we have such a large difference, improvement in accuracy that to me just feels like a natural decision. I don't really have to justify that it just optimizes less well. I'm sure people could try. But also you'll see qualitatively the results, like it just finds more random words. It's less specific because it's also like working over words, whereas we can actually have phrases since the language model generates phrases. We can be much more specific. So I think those are the advantages in general. But I'm really excited to get to the qualitative example. So maybe I'll hold questions for after, if that's okay. So before that, though, I want to introduce one more data set.
Yay!
This made him so happy.
Kiki and Booba.
Okay, so don't give it away, please. Anyone who doesn't know, could someone please take a guess at which one of these is Kiki and which one is Booba? Does everybody know? Kiki? Okay, great. Yeah, so in the 1920s, psychologists discovered this effect, where basically for gibberish words, we had visual associations, even though they meant nothing. And so we actually thought, well, this would be a really neat testing bed for our method, right? Because Clip probably doesn't know about these words. So Kiki and Booba actually kind of knows about it just because it's so famous, but other words, other gibberish words, I definitely won't know about it, and nor will the language model. Actually at NERPS in 2023, there was this generative model that learned to create, I'm sure everyone's familiar, but yeah, learned to create these visual images from gibberish words. And so we created 2 different data sets, each with 5 words to make it similar to iNaturalist setup. And we evaluated our method against the baselines, and we had very, very good performance, which makes sense, right? Because class name isn't going to work as well, or like zero-shot attributes definitely won't work because language model has no idea what these words mean. And we really have a large improvement in performance. So now, yeah.
Isn't the point of the paper that generates this data is that Clip kind of knows that or something?
I think it knows Kiki and Booba, but I don't think Clip
it doesn't. They don't know like
the other ones. I think it's just because Kiki and Booba are so famous now, right? But I don't think it knows the other ones. Yeah. Okay. So qualitative.
Do are you going to show some examples?
That's cool. Yeah, I'm getting.
All right.
Yeah. Oh, actually, I lied. One more slide, and then I'll get there.
All right.
Sorry. So confidence measure, we just wanted to show that our method is more confident than the baselines, and the way that we do that is we plot the margin, and the margin is just the difference in the top prediction for the class. So you take the mean, remember we take the mean Clip score across the attributes for each class, and the one that's the top is the top, and then you have the runner-up, and you take the difference in the mean between the top and the second, so the runner-up. And that represents confidence, because if it's a small margin, then on a random image, there's a chance that you just stumble over into the second class. But if it's large, it's very unlikely that that would happen. And so you see that our method is much more confident than the baselines. Okay, you guys have all been waiting very long for this. So qualitative results. Here's an example on the lichen family. So I'm only showing 5 of them. There's actually 7, but just so that visually pleasing. The first thing you're immediately going to notice is that all of these attributes are very focused on the structure, right? So, for example, stalked, gland-dotted leaves, furry velvety stems, block-like bracts, petal-like leaves, many-stemmed tree, twigs with clusters of small oval-shaped leaves, large clusters, blah, 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 blah. So the point is, it's really focused on structure. Why not color? Why not environment? Well, because these are not discriminative features. They all share the same color palette. They all share the same environment. Another kind of neat thing that I want to point out before we get into more technical things is it discovers hairy crown, which is kind of cool because that's the analogy that humans gave for this class. So I thought that was kind of cute. And then another thing you're going to notice is there's a lot of random words in here, right? So wispy, feathery foliage, elephant hide. Like, why are we talking about elephants right now? But if you actually Google these things, you'll see that it makes sense because the texture and structure are very similar. So it's actually very hard, as Alyosha will probably say, to give a textual description of exactly this texture. Yeah, lack of a better word. But if you were to say, oh, this is like the texture of an elephant, then it would be much easier. And so actually, it's kind of neat that it discovers some analogies here, in addition to discovering, adjectives and adverbs and so on.
I know we had a hard time with this, but I think if you gave us 400 iterations, we would have got it.
I feel like you would have gotten there.
Maybe
And maybe 8 hours instead
Yeah,
of 100.
exactly.
Yeah, if you guys do better than 8 hours, you're already better than my algorithm, so there you go. Question?
Yeah, I'm wondering, have you thought about fine tuning on these descriptions now that you have them? Like, it's like instead of having to wait 8 hours for the next one,
Yeah.
if you like fine tune a bunch of examples, maybe you can distill it.
Totally, so you want to fine tune which part, the LLM or the vision language model?
The vision language model. So it's like
Totally.
you give it a bunch of these images in
Yes.
context
Yeah.
and then give it this description as like fine tuning data and see if it can now like
Yes.
zero shot new things.
I think that would be super cool. I've thought about that. I also thought about if you decided that you knew that you wanted a particular type of description, like if you knew that you only wanted adjectives or you knew that you only wanted analogies, imagine retraining CLIP, but with only access to texts that fit that. So imagine like you ask a language model like, oh, like give me only like adjectives to describe this for every single class, for a lot of, not class, because CLIP isn't trained on class, but on a
Yeah.
lot of words. And you fine tune that. Now you can also guide the discovery. I know this is slightly different than what you were saying.
Couldn't you
Directions.
couldn't you get that actually just by changing your evolutionary algorithm? Like when you prompt it to generate
Yeah.
things, you could like prompt it to like only generate things with certain properties.
Yes, but the thing is, because we're doing evolution and there's a lot of iterations, that becomes very expensive for like GPT-4 and stuff. And with Llama, I actually wasn't able to control that so
I
neatly
see.
yet. But Llama 3 came out, and apparently this 8 billion parameter one is better than 70B. I don't know if you guys saw that, but anyway, so you guys should all swap to Llama 3, 8 billion instead of 70 billion if you want improvement in results and speed and memory and so on. Okay, I want to show Kikibuba results.
Yeah.
So what's kind of immediately obvious to me when I look at this is that it's no longer fine-grained classification. These objects or concepts or things are very different from one another. And so because of that, I actually think that the discovered attributes are much more object-oriented. And I think that's because like the decision boundary of latching onto an object is easier enough, and it already gives you high enough accuracy that it doesn't need to go into like finding very specific, detailed adjectives to delineate between the classes. And I just want to point out that it probably knows about Booba and Kiki. And then I think Galaga is actually an airplane. It's a game, I think someone told me that in my last talk.
Yeah.
But anyway, on my website, there's another slide that has other ones that are definitely not existing. And then Kipika and Maluma for sure don't exist. So there you go.
Wait, so each one of these is the top one or the better one?
Oh, these are just representative images from the data
No,
set.
the attributes.
What about them?
So are they all corresponding to
Galaga, yeah.
the top one?
Well, both of
Both of
them.
them are Galaga.
Oh, I see,
Yeah.
got it, I see.
Yeah. Cool. So I'm gonna move on quickly, but I can go back to these at the end of the talk if we have some more time.
Fluffy too. Not very fluffy.
No, it's not very fluffy, no, but I think it's kind of tail-like, so, I think it's latching onto that.
I'm not sure I like this model, like, I'm not, it seems like these two are very different. Or like, basically all the pairs are kind of different.
Yeah, I mean, I know that this data set isn't perfect for what I'm trying to show. This is kind of a product of just the data set. But it's also neat to see how the algorithm adapts when there's a lot of inter-class variability. Which I guess to me, it's not the best case. It's not really, so some future work I want to do actually is I want to discover clusters within a class so that you can say, okay, like this is actually one cluster, like because.
But you could just do just one image per class,
I
right?
could do that, yeah, I could.
Because
do
that might actually give you better results.
Yeah, but then at that point, it's no longer really a classifier, and we wanted to do classifiers first, right? Because then it's like a
Instant
single image.
classification.
It's instance classification, but then, yeah, I guess, I don't know, it's just you can't test on a test set then,
I see, I
Yeah,
see, I
but
see.
anyway, I agree that this is like, the results are worse. And I think that what I'm learning from this is that it doesn't work super well when there's a lot of intra-class, whatever the one on the inside is, variability, and that's where I want to work on supervised discovery of clusters within a class. Okay, so let's just show some qualitative results against the baseline. So people were asking about the gradient-based approach. So here are some discovered attributes for these two different classes. So we have for the panicled bulrush, we have thread, airplane, finishes, pile, hairy, tangle. So just you get a flavor of the fact that these words are much less descriptive and kind of arbitrary sometimes. And that's all I really want to show with this slide. I'm going to speed through a little bit for the sake of time. I wanted to show the prediction. So here for this particular image, for example, our method correctly predicts it as wellgrass. And we're showing the results on classification by description, and it predicts it incorrectly. And this is the classification by description for the right class. And the reason I want to show that is I want to show the contribution of each individual attribute. Something that I wanted to point out is this is really relevant to what you were saying, Yossi, about the fact that the language model doesn't know what the other classes are. So actually, it gives similar attributes, shares attributes across classes. For example, here with wood clubbrush, we have green or brown in color, green or brown in coloration. We have grows in wet or marshy areas, grows in wet or marshy areas. So one thing I could try is I could say, okay, tell the language model what are the 5 classes and now give me attributes. And I will do that actually before, probably for the rebuttal. But I still think that the fact that we're learning this gives it a larger advantage, and I don't expect that to get us to a point where we're no longer state of the art. But I will do that. That's a good point. And then I also wanted to show just the class probability. So there's 5 classes in this particular family, 5 species. This is the second class, and this is just a detail, but remember the margin metric where we were much more confident? That's reflected in a lot of these probability distributions, because you can see that, for example, for this class, for this image, probability distribution is much peakier than classification by description, which is much more uniform. And then this is kind of one of my favorite parts of the project. I think what's cool is we can actually, what's unique to this method is we can do explicit dataset bias auditing. So all of these plants in this family live in wet or humidish environments, except for the squirrel tail. And the discovered attributes for the squirrel tail are desert lavender, creosote bush, Arizona barrel cactus, sand sagebrush, spiny hedgehog cactus, and teddy bear cholla. So immediately this looks weird, and you can tell, oh, well, this informs me about the dataset bias in squirrel tail. I now know that in these pixels, there's something that's really making my algorithm latch on to some desert-y vibes. And that's cool because we had no prior knowledge that's coming straight from the pixels. And also because we have this bottleneck that's very easily interpretable, not like visualization of a bunch of images. It's just these words. We actually directly get that interpretability very easily, accessibly. And future directions. I'm so excited to talk about these. So attribute evaluation, so that's a really good point. We're doing some studies. I think that's gonna be really informative to us on like, where do we want to take interpretability next? Second is my most excited future direction. I'm most excited about this future direction. It's now I want to do programs. I want to discover not just attributes, but literal code generation to explain the world, right? Imagine, I can talk about this more in the one-on-ones, but basically moving on from classification, like how can I actually get machines to teach me about the world by capitalizing on all these existing models that we have, like segmentation, tracking, etc. And then finally tasks, like you can actually do this on different types of classification. Imagine you had like motion clip, then you can now do it like motion behavior analysis, and so on. So there's a bunch of stuff that we can talk about in the one-on-ones. And lastly, I wanted to thank my collaborators, Utkarsh and Carl, and also wanted to thank you guys. And I wanted to say that I'm inching to the end of my PhD slowly but surely, and so I'm open to some research hitchhiking.